So you should remember L'Hopital's rule from last year, or whenever you took Calc 1 if you weren't in my class last year. So you should remember that if, if your original limit is indeterminate in the form 0 over 0 or infinity over infinity, then you can take the derivative of the numerator and the derivative of the denominator and reevaluate that limit. And we should also remember that if we do that and the result that we get is still 0 over 0 or infinity over infinity, then we can continue to do that as many times as we need until our result is not one of those indeterminate forms. Everybody good with that? Hopefully so. All right. I'm not going to go through and prove it because we proved it last year, and trying to get through as much as we can in the short period of time that we've got. So let's take a look at a couple of them. These should be pretty straightforward, easy ones. Earlier this year, we've been factoring things like the limit as x approaches 2 of x squared minus 4 over x minus 2. But now when we plug in, we should be able to see that this is 0 over 0. And we should be able to then use L'Hopital's rule. And remember that when you do this, you need to indicate that you've used L'Hopital's rule. I'm just putting an LH, but write it out. Actually write out L'Hopital's rule. They really want to see that that's what you're doing. And you just take the derivative of the numerator, 2x, take the derivative of the denominator, 1, and then plug it in, and you get 4. Everybody good with that? Any issues with that? All right, what about the next one? Limit as x approaches 0 of root 1 plus x minus 1 over x. First thing you should do is what? Wow, lots of people typing in the chat. Plug it in. Good. What do you get when you plug it in? It's 0 over 0, right? So we get our indeterminate form here. So we will, using L'Hopital's rule, we will say that this is equal to the limit. I don't know why I wrote H. X approaches 0 of, what's the derivative of root 1 plus x? That should be 1 over 2 root 1 plus x times the derivative of 1 plus x, which is just 1, minus the 1, which is 0, and then all over 1, so I can ignore writing that. And what do we end up with? When you plug in 0, you get 1/2. Everyone good? Any questions there? This is what you should be teaching your 7-year-old sister, Nick. This is like real math almost. Getting closer at least. All right, let's take a look at these ones. Sorry, I'm a little distracted because my son's got his he's got his Zoom going. He doesn't have his headphones in, so I can hear everything. And there's some parent in the background like yelling at their kid to sit down and pay attention. And it sounds like me yelling at him to do that, except it's not me this time. And he's always muted at least, but that parent forgot to mute their kid's laptop. All right. Let's plug it in. What do we get if we plug in 0 here? It's 0 over 0. Yeah, 10 years from now, Nick, when she's in my class, I will teach her. I don't teach elementary school. Unless your parents are willing to pay me. My tutoring fee is like $200 an hour, though. So using L'Hopital's rule, what do we get? We end up with the limit as x approaches 0, still 1 over 2 root 1 plus x. And then minus 1 still goes away, and then minus 1/2 up there, and then over 2x. And when we plug in 0 over 0, what do we get? Still sorry, when we plug in 0, we still get 0 over 0. And then using L'Hopital's rule a second time, we'll end up with, let's see, so this first one, that minus a half is going to go away, and the over 2x is going to become just over 2. So what we have here, we have 1/2. I'm going to do this in a slightly different color here. This right here is 1/2 of 1 plus x to the negative 1/2. So that should become negative 1/4 of 1 plus x to the negative 3/2. Everybody good with that? And if we plug in our 0 into this, the 1 plus 0, 0. 1 plus 0 is 1, to the negative 3/2 is still 1, so we got negative 1/4 divided by 2, or negative 1/8. Good or no? All stuff you should have been able to do already before I started talking at all. Our favorite one that we didn't this year end up spending 15 minutes proving using areas of triangles and areas of sectors of circles. But now, super easy to figure out this one, even though we already know it's 1. Right? Using L'Hopital's rule, this becomes the limit as x approaches 0 of cosine x over 1, or just cosine of 0, which is 1. All right, everybody good there? We know that that one's 1. We already knew that one's 1, but we can use L'Hopital's rule to show it. Everyone good? All right. What about this one? What happens if we plug in pi over 2 here? What's the secant of pi over 2? What's secant of pi over 2? Right, it's undefined, but we know that as we approach pi over 2, we're approaching a vertical asymptote, so we're approaching an infinity value. So that numerator is infinity. And what about the denominator? 1 plus tangent pi over 2. Tangent of pi over 2 is also undefined. It's approaching a vertical asymptote, so 1 plus an infinite value is still an infinite value. So we've got infinity over infinity here. So we'll use L'Hopital's rule. Limit as x approaches pi over 2 of derivative of secant is secant x tangent x. And the derivative of 1 plus tangent is secant squared. And if we were trying to plug in pi over 2 again right away, what would we get? We'd still get infinity over infinity. So we should try to simplify this. First off, a secant and a secant will cancel. So this is the limit as x approaches pi over 2 of tangent x over secant x. And we could rewrite this as the limit as x approaches pi over 2 of sine x over cosine x all over 1 over cosine x, which is just the limit as x approaches pi over 2 of sine x. And as x goes to pi over 2, what is sine approaching? Sine of pi over 2 is 1. Everybody good? All right, you guys do this one real quick. All right, sorry, I was trying to help my kid with his laptop real quick. The video his teacher's trying to show him is like all staticky. So we plug in infinity, what do you get? You get infinity over infinity? Yeah? And we should know which one of those is growing more rapidly to be able to figure this out, but we could still take the derivatives using L'Hopital's rule to figure it out. This should become the limit as x approaches infinity of 1 over x over 2 over 2 root x, or just 1 over root x, which ends up becoming, as we simplify that down, what? Root x over x, or just a limit as x approaches infinity of 1 over root x, which is 1 over infinity, which is 0. Everybody good there? Is that what you all got when you did it? All right, cool. So now we're going to move into some other indeterminate forms that we would not have talked about last year in AB. So we're going to start with infinity times 0, or 0 times infinity. I probably briefly talked about this, mentioned a little bit last year, but we're gonna deal with it again this year. So we've got the limit as x approaches infinity of x times sine of 1 over x. So if we plug in infinity to both of those, this is going to give us infinity times the sine of 1 over infinity, or the sine of 0, so infinity times 0. So this one is a new indeterminate form for us, and how are we going to go about solving this, do you guys think? A couple different ways we could do it. Any ideas? Any ideas? Okay, so you want to make x to the negative 1. So effectively, you want to turn this into the limit as x approaches infinity of sine of 1 over x. And if that's x, bring it down to the denominator, make it x to the negative 1. So over 1 over x, is that what you mean, Shayla? Cool. Okay, good. So Nick, I see you said the squeeze theorem. Squeeze theorem is not going to work here because we'll note that we're approaching infinity. We're not approaching something like 0. So if that was approaching 0, yeah, you could definitely use squeeze theorem for it. But if we're approaching infinity, then there's no, we could theoretically use the squeeze theorem here, but it's going to be pretty difficult to find a function that's always above it and always below it that have that same horizontal asymptote. So it's possible, but it's not likely that we'll find it real quick. So now that we've got this as sine 1 over x over 1 over x, what form is this in? This is now 0 over 0. Everybody agree with that? Okay. And so then we'll do, using L'Hopital's rule, we should get the limit as x approaches infinity of the derivative of sine of 1 over x is what? Cosine of 1 over x times the derivative of 1 over x, which is what? Negative 1 over x squared. And then divided by the derivative of 1 over x, which is negative 1 over x squared. Cancel those out, and as we go towards infinity, this becomes the cosine of 0, which is just 1. Everybody good with that? Any questions on that? Everybody good with that? Okay, I'm waiting, Molly. because we're looking at a limit as x approaches infinity, not a limit as x approaches 0. The limit as x approaches 0 of sine x over x is 1, but not as we approach infinity. Now, one thing we could have done with this is when we wrote it like this, sine of 1 over x over 1 over x, I'm going to put in a new page here. We had this. We had the limit as x approaches infinity of sine of 1 over x over 1 over x. And I would imagine most of you probably might have for a second thought, oh, that's 1 for sure because it's sine of something over that same thing. We could do a substitution. We could let u equal 1 over x. And if we let u equal 1 over x, well, as x goes towards infinity, what is u approaching? Oops, I wrote 0 approaching. As x goes to infinity, u approaches 0. Exactly, like we're going to do that u sub. And then it ends up being a limit as u approaches 0. And in fact, it's approaching 0 from the right-hand side. We'll be as specific as possible because 1's positive and infinity is positive. Sine of u over u. And in that case, now we're approaching 0, Molly, so that we could say that's 1 now. But either way works. So there's not always just one specific way to solve some of these new indeterminate forms. Especially the 0 times infinity ones, you can usually find a couple different ways to rearrange them. For some of the other ones, there's really only one way to go about it. But everybody good with that one? Both ways of that? I mean, I specified 0 from the right because it is. Right? 1 is positive and x is going to infinity, so it's positive. So both the numerator and the denominator of that are both positive, which means when I divide, it's going to be approaching from the right-hand side. If I hadn't specified that, we'd still get the right answer, but we wouldn't be, we wouldn't be being as specific as we possibly could about that limit. All right, let's take a look at this indeterminate form, infinity minus infinity. And infinity minus infinity is one we might have dealt with a little bit. In fact, I think we did a couple problems with it earlier this year, like where we had the e to the 12x plus e to the 7x plus 8e to the 3x minus e to the 4x, you know, that kind of stuff. And we had to factor out the highest power. Some of those were infinity minus infinity ones. But so is this one. It's slightly different style of problem. The other one we knew we needed to factor. But for this one, we're going to have to find another method. So let's plug it in, make sure. If x is approaching 1, 1 over natural log of 1 is 1 over 0, so that'll be infinity. And minus 1 over 0, so that'll be infinity. So yeah, this is definitely infinity minus infinity. Everybody good with that being infinity minus infinity? Okay, so our goal when we have something like infinity minus infinity is still to turn it into something that we can apply L'Hopital's rule to, something that is 0 over 0 or infinity over infinity. So any thoughts on how we can rearrange this function so that we might get 0 over 0 or infinity over infinity? Yep, yeah, that's right. We're going to make a common denominator, so that'll be natural log x times x minus 1. So no L'Hopital's yet. Our common denominator is x minus 1 times ln x. So we're going to get x minus 1 minus ln x over ln x times x minus 1. Everybody good with that as our simplified fraction with the common denominator? And if we plug in 1, we got 1 minus 1 is 0, minus the natural log of 1, which is also 0. So we got 0 over natural log of 1 times 0, which is 0 times 0, so 0. So now we can use L'Hopital's rule. So using L'Hopital's rule, this should become the limit as x approaches 1 of, if we take the derivative of x, that's just 1. take the derivative of -1, that goes away. And the derivative over a natural log of x should be -1 over x. And then put that all over the derivative of this, which we'll have to use the product rule for. So natural log x times the derivative of x minus 1, so that's just 1, plus, and then the x minus 1 times 1 over x. Everybody good with that so far? All right, so then what? Plug it in again. We got 1 minus 1, which is 0, over 0 plus 0, right? We still have 0 over 0. So any thoughts on what we should do with that? Yeah, so we could use L'Hopital's rule again right away. Some of this is going to be a little bit of a pain, right? Like with our x minus 1 times our 1 over x. It might be good if we were to simplify our complex fraction first, and then if we need to, we can use L'Hopital's rule again. So let's simplify first and then use L'Hopital. So if this has an over x and this doesn't, I could get them both over x. And if I got everything in my denominator over x, then I should be able to cancel out those denominators. So if I multiply 1 by x over x, and if I multiply natural log of x by x over x, then everything's got an over x to it. Everybody agree with that? And we can eliminate all of the denominators. So this will give us the limit as x approaches 1 of x minus 1 over x ln x plus x minus 1. Everybody good with that so far? Okay, and if we plug in 1, we're still going to get 0 over 0. So we'll use L'Hopital's again now, Darius, and that gives us what in the numerator? Just a 1. And in the denominator, we're going to have to take the derivative of x ln x. So derivative of x ln x should be x times the derivative of ln x, which is 1 over x, plus ln x times the derivative of x, which is just 1, and then plus the 1 from the x, and the minus 1 goes away. Everybody good with that? And now when we plug in x equals 1, what do we get? We get 1 over 1 plus 0 plus 1. We get a half. Could I use a u substitution for 1 over x? Let's see, Vaishnavi. You're talking about, could I do that right here in this one where we got the common denominator? Let me see, that'd give you 1 minus u. I don't think that's going to be the best plan, because then you're going to have this x and this x that you're going to have to turn into 1 over u. So you'll have natural log of 1 over u plus 1 over u minus 1. You're still going to end up with a complex fraction. And I have a feeling that it's going to get more complicated than this did. I could be wrong, but I think it would. So I'd recommend getting the complex fraction simplified first and then seeing what happens from there. If you got that simplified down and then it looks like there's a nice substitution, then go for it. There's nothing wrong with trying it. So yeah, Aiden, they really want you to actually write out L'Hopital's rule instead of just writing LH. It's like some big point that they've been making over the last year or so. They really, really wanted to say L'Hopital's rule. I mean, if you spell it right, that's nice, but if you don't, I don't think they're gonna you know, I don't think they're gonna penalize you for spelling, but I could be wrong. I would say I've been wrong before, but that's not true. All right. Next indeterminate form is 1 to the infinity. So I got a lot of stuff written up there. For our indeterminate form of 1 to infinity, we're going to use a little trick that involves natural logs and exponential functions. So if I were to be looking for the limit as x approaches a of the natural log of a function, and it had a limit of L, let's say, then I could say that the limit as x approached a of just the function that was inside the natural log should be equal to the limit as x approaches a of e to the natural log of f of x, right? Because e to the natural log of f of x is the same as just f of x. Would you guys agree that e to the ln f of x is the same as f of x? Okay, so if the limit as x approaches a of ln f of x is L, and I have an ln f of x as part of my limit here, then I should be able to substitute that ln of f of x as L and say that the limit as x approaches a of just the function that I have is equal to e to the L. Does that conceptually make sense or no? All right, so what we're going to do is we're going to look at some functions that are just functions. And what we will do is, since this is in this indeterminate form of 1 to infinity, instead of trying to find this limit directly, we're going to take the natural log of the function that we're looking for the limit of, find its limit, and then at the end, we will just exponentiate that answer to get e to whatever power it is, and that will be our limit. Does that make sense to everybody? Hopefully. All right, and so this function right here, 1 plus 1 over x to the x, what should the limit of that be? Hopefully that's a function you know the limit of already. We would have talked about it last year. You would have talked about it in your rigorous honors pre-calculus class that you took 2 years ago, had you taken that. What is this limit? You should know it off the bat. You should have seen this function or a function related to this one a million times already in your life. The limit should be e. The limit is e. Right? This is just your basic compound interest formula, right? Don't you guys remember this? We talked about this last year also. But if we were to graph this, we'd see that this has a horizontal asymptote of e. 1 plus 1 over x to the x as x goes to infinity approaches Euler's constant, e. So anyway, let's go in and algebraically figure this out. So plug in infinity and you get 1 plus 0, which is 1 to the infinity power. So since we see that this is 1 to the infinity, we know that what we need to do for this indeterminate form to put it into a form that we'll be able to use L'Hopital's rule for, we're going to look at, instead of this limit, we're going to look at the limit as x approaches infinity of the natural log of 1 plus 1 over x to the x, which would be the same as the limit as x approaches infinity of x ln of 1 plus 1 over x. Everybody good with that so far? All right, so then now if we try to plug in infinity, what do we get? We get infinity times the natural log of 1, which would be infinity times 0. So we've moved it out of our 1 to infinity form into an infinity times 0 form. This is a form that we should know how to deal with. We can do one of a couple of different things. What do you guys want to do with it? Two different good options here. We did one very similar to this earlier, right? Except I think it had a sign in it instead of a natural log. Okay, so we get the limit as x approaches infinity of natural log of 1 plus 1 over x all over 1 over x. And now what form is that in? That form should be natural log of 1, which is 0, over 1 over infinity, which is 0. So we got 0 over 0. So now, I'm going to give us a new page for this. Using L'Hopital's rule, this will become the limit as x approaches infinity of what? The derivative of natural log of 1 plus 1 over x should be what? Should be 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is negative 1 over x squared. And in the denominator, we had 1 over x. So the derivative of that 1 over x should also be negative 1 over x squared. And we can cancel out those negative 1 over x squareds to give us a limit as x approaches infinity of 1 over 1 plus 1 over x, which gives us what? 1 over 1? Or just 1? Well, that doesn't seem to be the answer that we were supposed to get, does it? Didn't we say that this limit should have been e? How come we got 1 instead of e? Exactly, Nick. So this tells us that the limit as x approaches infinity of our original function, which was 1 plus 1 over x to the x is equal to e to the first power, right? That 1 comes in there, and we just get e as our result. Okay, so a lot of times people will go through this whole process and forget to re-exponentiate their answer. Remember, we're looking at the limit of the natural log of our function. That limit was 1, so we exponentiated to get e to the first power, or just e. Everybody good with that? It is fun, Kiana. That's true. I agree. Any issues with that? Everybody okay? All right, let's do another one. So now we're going to look at 0 over 0. So we're looking at the limit as x approaches 0 from the right of x to the x. I think pretty obviously if you plug in 0 to that, you're going to get 0 to the 0. And we're going to use the same method that we did for the last one, where instead of looking at this limit, we're going to look at the limit as x approaches 0 from the right of the natural log of x to the x, which will give us the limit as x approaches 0 from the right of x ln x. Everybody good with that so far? And then we'll use the same process, because if we try to plug in 0 into this, this becomes 0. And as we approach 0 from the right of natural log of x, that's 0 times negative infinity. 0 times infinity or negative infinity is still indeterminate. So we'll rewrite this as the limit as x approaches 0 from the right of natural log of x over 1 over x. That seemed like a good way to go. Hopefully, and that's a negative infinity over an infinity. So we will use L'Hopital's rule here and end up with what? The limit as x approaches 0 from the right of 1 over x over negative 1 over x squared. And what does that become? The limit as x approaches 0 from the right of negative x. And as x approaches 0, what does negative x equal? Should be 0. So we need to then say the limit as x approaches 0 from the right of x to the x is equal to e to the 0 or 1. Everybody good with that? Don't forget to re-exponentiate it at the end since you've taken the natural log of your function to begin with. All right, let's take a look at infinity to the 0. So the limit as x approaches infinity of x to the 1 over x. Should see that that's infinity to the 0. No, Luke, there's not really a specific name for the rule. It's just a technique we use. I don't know. We could come up with a name for it if we wanted to. I guess I don't believe that there's a specific name that people refer to this rule as, though. We can call it the logarithmic exponentiation limit rule, or the batch method, I guess, or the Lime rule. What is that supposed to be? A limit with an E in it or something, Darius? I don't know. Okay, yeah. I don't like any of those names. All right, so same thing here. We're going to do the same thing. We're going to look at the limit as x approaches infinity of the natural log of x to the 1 over x, which is going to be the limit as x approaches infinity of 1 over x times natural log x, or just the limit as x approaches infinity of natural log x over x, which is what? That's infinity over infinity. And we know which one of those grows faster, so we know what this should come out to be, but let's algebraically show it. So this is the limit as x approaches infinity of 1 over x over 1. And as x goes to infinity, that's 0. And so the limit as x approaches infinity of x to the 1 over x is equal to e to the 0, which is 1. And you'll find a lot of the time these ones where we take the natural log will come out to be e to the 0 at the end. You'll end up with 1, but that's not always the case, so don't assume that will always be true. And don't fall off your mouth that way. Everybody doing all right with these? We'll do a couple more. All right, what about this one? Is this one of those determinate forms that we have been talking about? 1 over 0 should be infinity, right? To the 0. That's on our list, right? That's the one we just did, isn't it? Infinity to the 0. So we will look at the limit as x approaches 0 of the natural log of 1 over x squared to the x, which is the limit as x approaches 0 of x ln 1 over x squared, which is now what form? 0 times natural log of 1 over 0, and that'd be natural log of infinity. So 0 times infinity. And again, we'll rewrite it using, well, not using L'Hopital's rule yet. We'll rewrite it as the limit as x approaches 0 of natural log 1 over x squared over 1 over x. And then we'll use L'Hopital's rule. Everybody good with that or no? All right, and if we're doing the natural log of 1 over x squared, that's the derivative of that should be 1 over x squared, which is just x squared. And then times the derivative of 1 over x squared. 1 over x squared is x to the negative 2, so that should become negative 2 over x cubed. And then we're going to divide that by the derivative of 1 over x, which is negative 1 over x squared. And so if we simplify all of that down, what do we end up with? You get the limit as x approaches 0 of what? The negatives cancel, right? We're going to have a 2. And this x squared that's in the denominator of the denominator gets flipped up into the numerator of the numerator. So that's x to the 4th over x cubed, which is just x. Yep, Adrian, 2x. Good. And that equals 0. And so the limit as x approaches 0 of 1 over x squared to the x is e to the 0 or 1. All right. Why don't you guys give this one a try on your own real quick, see if you can come up with this one. How's this one going? You guys doing all right with it? Zero to the 0 power, right? You guys finished with this, or you still need a minute? All right. I'll sit here and shut up while you guys work. just have no attention span. I just get bored while I'm sitting here waiting. I can't answer that question, Adrian. Not everybody's finished yet, but it's very possible. You guys all ready now or no? Everybody good with the first couple of steps there? Okay. All right, hold on one second. All right, so then from there, if we plug in pi over 2, that's 0 times the natural log of 0, which is going to give us a 0 times a negative infinity. So we'll be able to rewrite this as what? What would you guys rewrite this as? Hopefully the limit as x approaches pi over 2 from the left of natural log cosine x over 1 over cosine x, or I would probably write it as secant x just because that'll be quicker and easier for us to take the derivative of. And you did a u sub for cosine. Yeah, that's fine if you did that, yeah, that's not a problem at all. So natural log of cosine, that's the cosine of 0, which is going to be infinity, and the secant of pi over 2, which is going to be infinity. So we'll use L'Hopital's rule to get the limit as x approaches pi over 2 from the left. We'll take the derivative, natural log of cosine's derivative is 1 over cosine times the derivative of cosine, which is negative sine, and then all over secant x tangent x, and the sine over cosine in the numerator is a tangent, which we'll cancel with a promise that said tangent there. We're going to rewrite it. That tangent will cancel with that tangent, and we got negative 1 over secant, which is just negative cosine x, and that just ends up giving us 0. And so we know that the limit as x approaches pi over 2 from the left of cosine x to the cosine x is e to the 0 or 1. Anybody have issues with that? Everybody good with that? I assume doing your u sub, you subbed out cosine and had natural log of u over 1 over u. Is that right, Kiana? It came out to be the same thing? Okay, good. All right, let's take a look at this one. If we plug in infinity, what do we get? should be infinity over infinity, right? So using L'Hopital's rule, this will become the limit as x approaches infinity of 1 over x plus 1 over 1 over x times what? One over x times the natural log of 2, right? We all remember how to take the derivative of log base 2 of x, I hope. And so then we can rewrite this in a simpler form, probably of x ln 2 over x plus 1. And as x goes towards infinity, this is still infinity over infinity. So we'll use L'Hopital's rule again to get the limit as x approaches infinity of natural log of 2 over 1, which is just natural log of 2. And is that our answer? Or do we need to exponentiate this? No exponentiating it because we didn't take the natural log, right? So just be careful. Don't get in the habit of just exponentiating a bunch of stuff. And then as soon as you come across one where you didn't take the natural log, make sure you don't exponentiate it. All right, we're going to do a couple more and then we'll be done. I was thinking we might end early, but I don't know. It's going to be only a minute or two now if we do. So let's look at this one. The limit as x approaches 1 from the right of x to the 1 over 1 minus x. You guys want to try that on your own? Okay, good. Try it on your own since no one's answering. You got 2 minutes. You guys finished? Another minute. I'm getting bored over here again, guys. Was that really only 2 minutes? Oh, geez. That felt like an eternity. Everybody good now? This is 1 to the infinity, so this is one of our natural log ones. So we're going to look at the limit as x approaches 1 from the right of, if I take the natural log of this, it's going to be 1 over 1 minus x times the natural log of x, right? And that becomes natural log of 1, which is 0 over 0, which means we can use L'Hopital's rule to get the limit as x approaches 1 from the right. The derivative of natural log of x is 1 over x. The derivative of 1 over 1 minus x, well, that's 1 minus x to the negative 1. Oh, no, it's just a 1 minus x. Never mind. Sorry, that's just a negative 1. And so what does that give us if we plug in 1? It should give us negative 1. And so the limit as x approaches 1 from the right of x to the 1 over 1 minus x is equal to e to the negative 1 or 1 over e. So there we go. We found one that wasn't equal to 0 and then became e to the 0 for 1. That's something else for 1. Yeah, it only works for the ones that we've talked about, Nick. It only works for the ones like, I got the whole list here, infinity to the 0, the ones that have powers in them, because it breaks up that power and makes it 0 times infinity usually. So infinity to the 0, 0 to the 0, 1 to the infinity. All right, last one of the day. Let's plug in our 0. What do we get? We get natural log of 0 from the right, which is infinity, and natural log of 0 from the right, which is another negative infinity. So we have negative infinity minus negative infinity, which effectively is infinity minus infinity, which is an indeterminate form, right? Infinity minus infinity. And in the last one, we found a common denominator, right? And combined them together to figure that out. But there's no denominators here, so that's going to be an issue. Any thoughts on what we might better do with this one? We're going to use some log rules. That's right. So the natural log of a minus the natural log of b is equal to the natural log of a over b. Right. So the limit as x approaches 0 from the right of the natural log of x over sine x. That's just using a log rule. And from here, yeah, we could just do a u substitution. What do you want to do? U equals, how about x over sine x? Yeah. And as u approaches, as x approaches 0 from the right, what is u approaching? That's when we should know, right, that we could use L'Hopital's rule for u approaches 1. And so we've got the limit as u approaches 1 of the natural log of u. And as u goes to 1, natural log of u is equal to 0. And then we exponentiate it? No, we do not. All right, we just get 0. Everybody good with that? Any issues or questions on these new indeterminate forms? How to use L'Hopital's rule once we get them? We're not really using L'Hopital's rule for a new indeterminate form. We're just manipulating indeterminate forms into 0 over 0 or infinity over infinity so that we can use L'Hopital's rule. But I'm guessing you guys would like some more practice with this. Whether you would or not, I'm going to post up an assignment with some of these limits. Some of them, most of them will be the new type, but we'll have some that are just like the regular old L'Hopital's rule ones. So you'll have a L'Hopital's rule assignment tonight. Other than that, we should be good for today. Expect, even though I haven't graded your first assessment, expect a short assessment at some time this week, Thursday or Friday this week, on anything we've talked about up until today. So not today's stuff, but the stuff between the end of limits. So continuity all the way through everything we did with the derivatives before L'Hopital's rule. Adrian, I would expect it to be at least slightly more difficult, but again, my goal is for the assessments to be easy and just test whether you have a basic understanding of how to do the work. I'm trying not to stress anybody out or kill anybody this year, like I normally would in the class. Molly, I haven't written it yet, so anywhere from 1 to 50. Who knows? Probably less than 50. Probably more than 1. Single digit numbers. Less than 10 even, let's say. Somewhere from 1 to 9 questions.